You've seen a little bit about synthetic division in class. Let's practice some more examples. This is certainly a fun and easy technique to get some answers quickly. Okay, so we want to take this polynomial and divide it by x minus 2. Remember how we set up our synthetic division. We want to make sure we get all of the coefficients represented, 1, 2, and notice there's no x squared term, so we have to fill in a column, -5 and -2. So always double check, fourth power, third power, second power, first power, constant. And remember, if we're dividing by x minus 2, we want to use the opposite of this value, so we put a +2. And we start our synthetic division. We bring down the value of 1, and then diagonally we multiply 2 times 1, and we add our column. We multiply diagonally, and we add the column, multiply, add the column, multiply, and add the column. And this value is our remainder. So what did we just find out when we take our original problem? Let's rewrite it as a solution. So we took this and divided by x minus 2, and what we came up with is our coefficients. Notice when we take x to the fourth divided by x, we've reduced this. So this will be x cubed plus 4x squared plus 8x plus 11. And then what do we do with our remainder? We can write our remainder over the divisor. So if our remainder is 0, that's when something unique happens. Our next question says to take our answer from problem 1, example 1, and write it in factored form. So look at the equation we wrote up above. Would it be sensible to say that we could multiply both sides of this statement up above to move this divisor to the other side? So another way of writing that statement up above, and this is really just taking the previous answer, and we're moving this, so it is x minus 2 times x cubed plus 4x squared plus 8x plus 11. And then when we multiply this term by x minus 2, notice that the x minus 2 would cancel if we multiply it by x minus 2. So there's another way of writing exactly the same statement as we had in example 1. Let's do another practice problem. We want to take this polynomial divided by x plus 3. So remember, the format for our synthetic division is we have to take the solution to this factor. So the solution to the divisor would be -3 if we set it to 0. And we set up our coefficients. 3 is our fourth power, fourth degree. There's no third degree, so we fill in with a 0. Second degree, first degree, 0 degree. Whoops, 0 degree is 1. And now we set up our synthetic division. We multiply diagonally, and then we add vertically. We multiply, and we add. We multiply these together, and it's okay if it's getting large. That's going to happen fairly often. So we would come up with a -102, and we would multiply these, -321, and when we add, we'll come up with a -320 if my arithmetic is correct, and that's fine. So now what have we found out? We're going to use these digits, and this time we're being asked to write it in factored form. Let me show you both forms again. So here's what we did. We took our original polynomial. We divided it by x plus 3, and we got this answer. So notice fourth degree divided by x is going to reduce it to a third power. So we're counting down 1 with our exponents. And then we could write this remainder, negative 320, over our divisor. That was our first way of writing our answer. But this direction said to write it in factored form. So what we're being asked to do is what we just did a minute ago. Let's multiply this to both sides. And that would be the factored form. So we would have just an alternate way of writing that. These two answers, these two previous steps are of course the same, but we multiply this term by x plus 3 and the denominator would cancel. So we'll just have a minus 320. Very easily done. All right. The remainder theorem tells us one of the reasons synthetic division is so useful. What if we get a remainder? What if we get a remainder? What are we actually finding? We are finding that the polynomial is divisible except with that little bit of a remainder, and that tells us the answer for f of k. Let's see what we're talking about here in example 4. Let's find f at 2 using synthetic division. So, and of course you can plug this into your calculator and check out what your answer should be. But let's quickly set it up with our remainder theorem. An important thing to remember here is that if we're finding the remainder, then we want to think of this as an x, a remainder when we put 2 here. So we want to set up 2, negative 5, 4. Everything is present here, every power. So we do our multiplication, add, multiply, add, multiply, add. So we believe that this conclusion tells us that f of 2 should be equal to 2. Now let's convince ourselves whether that's correct. If we do this the old-fashioned way, let's find f of 2. We would put 2 in for x and we would cube it, so we'd have 2 times 8 minus 2 times. We'd put 2 in and square it and we'd get 4. Put 2 into the next term and of course that'll be a minus 10. Well, let's check out our arithmetic here. 16 minus 8 minus 10 plus 4. So we come up with 2. So it didn't save us much arithmetic doing the synthetic division, but you can imagine if this were a 5th power or a 7th power, the synthetic division process is very simple, but the other evaluation process might require some large arithmetic values. Okay, so the remainder theorem, if we want to find the value of a function, we simply use that value in synthetic division, and our remainder tells us the y-coordinate when we plug that value in as the x-coordinate. So we now know that the point 2, 2 is on the graph of function f of x. All right. So what if that remainder turned out to be 0? Well, then, of course, the coordinate, the xy point, would have 0 as its y-coordinate, and that happens to be an x-intercept, and we call it a 0 of the function. So let's try one more type of question. Is negative 6 a 0 of this function? Well, let's find out if we do synthetic division. Do we get a remainder of 0? And there's our remainder of 0. So a remainder of 0 tells us several different things. We now know that f of negative 6 turns out to be 0. When we put negative 6 in for x, we got 0 for y. So negative 6, 0 is on the graph. So we would say that negative 6 is an x-intercept. It's not necessarily the only x-intercept, remember that? But that would help us to graph that polynomial if we can find all of its x-intercepts. We also say that negative 6 is a 0 of function f. And if we could find other zeros and learn a little bit more about that graph in our next lesson, then we'll know how to come up with graphs of curves instead of just graphs of straight lines.